Hello students, welcome to lecture 2 of S Block Group 1 Elements. Now our topic chemical properties. The alkali metals are highly reactive due to the large size and low ionization energy. So that first group elements having large size and low ionization enthalpy. Due to these properties, the alkali metals are highly reactive. And the reactivity increases from lithium to cesium. Lithium to cesium means the cesium having high reactivity than the lithium. The first chemical property, reactivity towards air. The alkali metals react with dry air to form oxides. Then react with moisture to form hydroxides. Moisture means H2O. React with moisture to form hydroxides. And here the lithium forms monoxides. So let me take the reaction. Lithium can react with air O2 and it gives lithium monoxide Li2O and balance that equation. So here 2 oxygens, so let me take here 2 and lithium become 4, so let me take here 4. So this is the monoxide. And sodium forms monoxide in limiting supplying of oxygen and peroxide in excess of oxygen. So that sodium can form monoxide and peroxide. So here that sodium react with limited supplying of oxygen. So here that oxygen is limited. Then it will give monoxide, sodium monoxide. And balance that equation, 2 oxygens, let me take here 2 and 4 sodiums, so here 4. And that sodium also can form peroxide by supplying of excess of oxygen. So oxygen is excess, so it can give sodium peroxide Na2O2. And the remaining metals means here I am taking M is equal to potassium, rubidium and cesium. So these 3 metals can form superoxides. Let me take the reaction. M plus oxygen gives rise to MO2. So it is a superoxide. So the lithium can form only monoxide and sodium can form monoxide and peroxide. With limiting oxygen, it can form monoxide. With excess of oxygen, it can form peroxide. And the remaining metals, potassium, rubidium, cesium, can form superoxides. In all oxides, the oxidation state of the alkali metal is +1. So that metal oxidation state is +1. So here lithium oxidation state +1 and sodium oxidation state +1. Potassium, rubidium, cesium oxidation state +1. So in all oxides, the oxidation state of alkali metal is +1. And lithium directly react with nitrogen of air to form nitride. So that lithium can react with nitrogen, then it can form nitride, Li3N, lithium nitride. And alkali metals are stored in benzene and petroleum ether, kerosene oil, because all these are the highly reactive, so that's why they are preserved in benzene and petroleum ether and kerosene oil, because of high reactivity towards the air and water. Next, second one, reactivity towards water. The alkali metals have large negative reduction potential values. Negative reduction potential values. So they can act as better reducing agents. Reducing agents. So they react with water to form hydroxides and H2 gas. Let me take the reaction. So here M metal means here M nothing but it may be lithium or sodium or potassium, rubidium, cesium, first group metals. So that M means metal react with water, then it can form hydroxide, MOH plus H2 gas, and balance that equation. So let me take here 2 and here also 2, then here 2. Now it is a balanced equation. So that metal react with water to form hydroxides and H2 gas, and the reactivity increases from lithium to cesium. From lithium to cesium the reactivity increases, and sodium sometimes catches the fire, and potassium, rubidium, cesium always catches the fire. And they can also react with alcohols, ammonia and 1-alkynes. Let me take that reactions. Alcohols, ROH. Let me take one metal, sodium. The sodium react with alcohol, then it will give sodium alkoxide, RONA, sodium alkoxide plus H2, and balance that equation. So here 2, let me take here 2 and here also 2. And that metals also react with ammonia. Let me take ammonia, NH3 plus one of the metal, sodium, then it can form sodamine, NaNH2 plus H2, and here 2, 2, and here also 2. Now it is a balanced equation. Next, 1-alkynes. The metals react with 1-alkynes, means acetylene. So HC triple bond CH, and plus I'm taking the sodium, then it will give NaC triple bond CH plus H2, and balance that equation. Here 2 and here also 2, then here 2. So the first group metals react with water to form hydroxides and H2 gas, and also they can react with alcohols, ammonia and alkynes. Next, third one, reactivity towards dihydrogen. The alkali metals react with dihydrogen at 400 degrees centigrade, but the lithium react with at 800 degrees centigrade to form hydrides. So first group metals react with dihydrogen to form hydrides, and all the alkali metal hydrides are ionic solids and having high melting point. High melting point. So let me take reaction M plus dihydrogen H2. So here M means it may be lithium or sodium, potassium, rubidium and cesium. So this first group metals react with dihydrogen to form metal hydrides MH on heating. But the lithium react with dihydrogen at 800 degrees centigrade. So here that metal get positive and hydrogen get negative. That metal hydrides are ionic solids and they are having high melting point. And the stability of hydrides decreases from lithium hydride to cesium hydride. So lithium hydride having high stability and the cesium hydride having less stability. So the stability of hydrides decreases from lithium hydride to cesium hydride because lattice energy decreases from lithium hydride to cesium hydride. Next one, reactivity towards halogens. So that alkali metals react with halogens to form ionic halides MX, but lithium halides are covalent due to the high polarization capability of lithium ion. So that lithium ion size is very small. So due to the small size, it can form covalent lithium halide. So the lithium halides are covalent due to the high polarization capability of lithium. So what is the polarization? The distortion of electron cloud of an anion by the cation is called polarization. Let me take the halides here. Lithium plus and here sodium plus and potassium plus, then rubidium plus and cesium plus. So if you go from top to bottom in a group, the size of cation increases. So the lithium having small size. So here the size is small and here the cesium size is large. And if you come to that halogens, so here the halogen general formula X minus. So here X minus and here also X minus and X minus, X minus and X minus. So these are the halides of first group metals. So here the lithium halide having covalent character because high polarization capability of lithium ion. So the distortion of electron cloud of the anion by the cation is called polarization. So here the polarization will takes place. So due to that distortion of electron cloud, its character is covalent character. So the lithium halides are somewhat covalent. And here less distortion takes place, then it is a ionic. And here also less distortion, so then the potassium halides are also ionic. And here no distortion, so rubidium halides are more ionic. and here there is no distortion. So the cesium halides are much more ionic. So the ionic nature increases from lithium to cesium with halogens. So ionic nature of first group halides increases from lithium to cesium. So the lithium halides somewhat covalent, sodium halides ionic, potassium halides ionic, and rubidium halides more ionic. Cesium halides are much more ionic, because here if you go from lithium to cesium, the size of the cation increases. If the size increases, the distortion of electron cloud on anion decreases. So the polarization capability increases with decrease in cation size. So the lithium plus size is very less, so its polarization capability is more than the sodium plus, and sodium plus having more polarization capability than the potassium plus, like that. And if you come to that anion, the electron cloud distortion increases with increase in anion size. So here the anion size increases electron cloud distortion increases. Electron cloud distortion increases. For example, if I take anions, I am taking 7th group anions: fluorine, chlorine, bromine, iodine. If you go from fluorine to iodine, the size of the anion increases. So due to the increase in size, the electron cloud distortion also increases. On this iodine, the electron cloud distortion is more than the Br minus and Cr minus and F minus. Now let me take that covalent nature of lithium halides. Lithium halides covalent nature. The lithium halides are lithium fluoride, lithium chloride, and lithium bromide, and lithium iodide. So here the cation is the same in all these compounds, but the anions are different: fluorine, chlorine, bromine, and iodine. So this is the increasing order of covalent nature. Covalent nature increases. Let me take the reaction. That metals react with halogens to form metal halides, Mx. So here M is equal to lithium, sodium, potassium, rubidium, cesium, and balance that equation. So here I'm taking 2, then here we have to take 2. So now it is a balanced equation. So the metals react with halogens to form metal halides. Next one, reducing nature. The alkali metals having large negative reduction potential values. Large negative reduction potential values. So they can act as reducing agents. Reducing agents. The first group elements act as a reducing agents. According to reduction potential values, the strength of metals, lithium is a strong and powerful reducing agent. So lithium greater than rubidium greater than cesium and greater than potassium greater than sodium. So here the lithium is a strong and powerful reducing agent, and sodium is a least powerful reducing agent. This reducing power depends upon the overall change, that are sublimation enthalpy, ionization enthalpy and hydration enthalpy. So sublimation enthalpy means here the metal is a solid. The solid metal is converted into gas metal. So here the energy required to convert 1 mole of solid into gas without being liquid is called sublimation enthalpy. So this is the sublimation enthalpy. And ionization enthalpy means the energy required to remove one electron from outermost orbital is called ionization enthalpy. So here the gas metal, and it lost one electron, then it will form cation plus one electron. So this is the ionization enthalpy. And next to hydration enthalpy, the energy released when 1 mole of ion react with water is called hydration enthalpy. M plus aqueous. So this is the hydration enthalpy. So the reducing power depends upon the overall change in sublimation and ionization enthalpy and hydration enthalpy. And that lithium has a small size and high hydration enthalpy, which leads to high reducing power. So the lithium having high reducing power because it has small size and high hydration enthalpy. Next one, solution of alkali metals in liquid ammonia. So the alkali metals dissolve in liquid ammonia, then give deep blue color. Deep blue color. This deep blue color is due to the ammoniated electron. Ammoniated electron. So what is that ammoniated electron? Let me explain. So here I am taking the beaker. In that beaker I am taking liquid ammonia. So this is the liquid ammonia. To that liquid ammonia I am going to add first group metals, means alkali metals. So then what happening? So that metal will give M plus electrons. So in that liquid ammonia the metal will lose one electron, then it can form mono positive ions. So after adding the metal in that solution, what are present? NH3 molecules and M plus ions and electrons. So here in this solution that M plus ions are surrounded by ammonia molecules, and as well as that electrons also surrounded by ammonia molecules. So here how that metal ions and electrons are surrounded by the ammonia molecules. Let me take. So this is the beaker. So in that beaker we have M plus ions and electrons, and also there are NH3 molecules in that solution. So this M plus ions surrounded by ammonia molecules. We know that ammonia NH3 so here the nitrogen will get partial negative charge due to high electronegativity, and that hydrogen will get partial positive charge, and here also partial positive and partial positive. So due to high electronegativity of nitrogen, the electrons are tendency towards the nitrogen. So the nitrogen will get partial negative charge and hydrogens will get partial positive charge. So here that metal having positive charge and nitrogen having negative charge. So there is a attraction between the positive and negative. So here also I am taking another molecule. Here also attraction between the positive and negative, and here also another molecule and attraction between the NH3 and metal ion. So this is called ammoniated metal ion because that metal ion surrounded by the ammonia molecules. So it is called ammoniated metal ion. And here this is the electron. So in that solution also we have electron. That electron also surrounded by ammonia molecules. So here NH3. So here hydrogen, hydrogen and hydrogen. That nitrogen will get partial negative and hydrogen will get partial positive. And here also partial positive and partial positive. Then that electron having negative. So there is attraction between the positive and negative. And here also another molecule NH3. Hydrogen, hydrogen, hydrogen. And attraction between the electron and hydrogen. And here also NH3. So attraction between the electron and hydrogen. So this electron is called ammoniated electron because that electron surrounded by ammonia molecules. So that's why it is called ammoniated electron. So due to this ammoniated electron, the solution will get deep blue color. Let me take the reaction. So metal plus X plus Y moles of NH3 molecules. So there are so many NH3 molecules in the solution. So here I am taking X plus Y moles of NH3. So then what happening? The metal will give M plus ions and electrons. So M plus and plus electrons. And that M plus ion surrounded by NH3 molecules. So here NH3 molecules. So how many moles of NH3 molecules? X moles of NH3 molecules. So here X moles of NH3 molecules. That electron surrounded by NH3 molecules. So how many NH3 molecules? Y moles of NH3 molecules. So M metal plus X plus Y moles of NH3 gives rise to M plus NH3 taken X times plus electron and NH3 taken Y times. So this is the ammoniated metal ion and this is the ammoniated electron. Due to this ammoniated electron, the solution will get deep blue color. And the solution is paramagnetic. The solution of alkali metals in liquid ammonia is a paramagnetic. And strongly reducing solution. It is a strongly reducing solution because there are unpaired electrons. So due to that unpaired electrons, the solution get paramagnetic nature. So the solution is a paramagnetic and strongly reducing solution. and on standing, the solution slowly liberate H2 gas and form a amide. So let me take that reaction. So in that solution we have ammoniated metal ion plus ammoniated electron and ammonia molecules gives rise to NH2 and plus of H2 gas. So on standing, the solution slowly liberate the H2 gas, and on warming, the concentrated solution deep blue color changes to bronze color. On warming, if you heat that solution, on warming, the deep blue color changes to bronze color, and paramagnetic becomes diamagnetic. The para become dia because the electrons going to be pair. So due to the pairing of electrons, the magnetic nature is diamagnetic. Next, uses of first group elements. So the lithium metal is used to make a useful alloys. So the lithium used to make the alloys. For example, the lead is used to make the white metal. And this white metal is used in the manufacture of bearings. So these bearings are used in the motor engines. And lithium with aluminium is used to make the aircraft parts. And the lithium with magnesium is used to make the armor plates. These armor plates are useful to soldiers to protect the body in a battle. And lithium used in thermonuclear reactions. And used in the making of electrochemical cells. The sodium lead alloy needed to make the tetraethyl lead and tetramethyl lead. So this tetraethyl lead and tetramethyl lead is used as a anti-knocking agent. In petrol to decrease the friction. So to decrease the friction, that tetraethyl lead and tetramethyl lead are useful. So these are called anti-knocking agents. And the liquid sodium is used as a coolant. in nuclear reactors. And potassium has a vital role in biological systems. And KCl is used as a fertilizer, and KOH used as a excellent absorbent of carbon dioxide and used in manufacture of soft soap. So the KOH is used as a excellent absorbent of carbon dioxide and used in a manufacture of soft soap. So these are the uses of first group elements.